This session is about logic families. Any logic circuit consists of diodes, resistors and transistors. Initially, these logic circuits are implemented using discrete components. But as the complexity of the circuit increases, they has to be converted into integrated form. Depending upon the components which are used for the fabrication, these logic circuits are classified into different logic families. In this module, we are going to learn about the electrical characteristic, classification and the evolution of logic families. Let us understand the learning objectives of this module. To understand the logic families, to know about the significance of logic families, to identify their different characteristics, to classify them and to know the evolution of logic families. Logic families. A group of compatible ICs with the same logic levels and supply voltages. Fabrication using a specific circuit configuration. That is, specific circuit configuration including different components has to be considered while fabrication. Same basic logic circuit during the fabrication means when a particular logic family is considered, one has to consider the basic logic circuit either of only diodes and resistors or only transistors, like that. Simple components like resistors, diodes, transistors and MOSFETs has to be used while the fabrication of these logic families. Let us know about the significance of logic families. That means why these logic families are so important. The first and the most important is the simplicity in the design, because the basic components like diodes, resistors, transistors are used during the fabrication. Members belonging to the same logic family has similar electrical characteristics. Even if the circuit is complex, these logic families definitely reduces the complexity of the circuit during the design of that particular application. It provides the compatibility of the digital circuits during the fabrication. And of course, easily expandable. Let us see how these logic families are classified. They are classified into two types: unipolar and bipolar. In unipolar, they are classified as PMOS, NMOS and CMOS, which specifically uses MOSFET as the basic component. In bipolar, non-saturated and saturated, specifically transistors are used during the fabrication of bipolar logic families. Non-saturated bipolar logic families are further classified depending upon the speed of operation, that is Schottky TTL and emitter coupled logic. Saturated bipolar logic families are classified as RTL, that is resistor transistor logic, DTL, that is diode transistor logic, and TTL, that is transistor transistor logic. Let us see in detail which components are used in different logic families. If one consider DL, that is diode logic, then diodes and the resistors are the basic components used in the fabrication. RTL, resistor transistor logic, then resistors and transistors are the basic components which are fabricated. In DTL, that is diode transistor logic, diodes and transistors are used during the fabrication. And in TTL, transistor transistor logic, transistors are the basic building blocks during the fabrication. ECL, that is emitter coupled logic, uses again transistors and diodes. PMOS, that is P channel metal oxide semiconductor logic, uses P type MOSFETs or P channel MOSFETs. NMOS uses N channel MOSFETs. And CMOS is the combination of P and N MOSFETs. So, both the components are used during the fabrication, that is P MOSFET and N MOSFET. Let us see different types of logic families. Logic families are classified based on the number of logic gates fabricated per chip. That means how many logic gates are there per chip. So, logic family are classified accordingly. If we consider only 12 gates per chip, then it is called as small scale integration, that is SSI. If nearly 100 gates per chip, MSI, that is medium scale integration. More than 1K gates, then LSI, that is large scale integration. And more than 10K gates, that is VLSI, very large scale integration. Let us consider the logic levels which are used in digital electronics. Binary signal has two values, logic 0 and logic 1. These are interpreted in logic levels as positive logic and negative logic. When we consider positive logic, high is considered as logic 1 and low is considered as logic 0. In negative logic, the reverse is the case, that is high is considered as logic 0 and low is considered as logic 1. You can see this on the slide, how it looks. For positive logic, you can see that the logic value is 0 for low and 1 for high. And for negative logic, logic value is 1 for low and 0 for high. Interpretation of positive and negative logic. Positive logic inputs and outputs are referred as active high signals. And negative logic inputs and output signals are referred as active low signals. So, in circuits, they are interpreted as no bubble for the positive logic, that is active high, at the input or outputs, and bubbles at the input and output for the negative logic, which is referred as active low. Let us consider the example for positive and negative logic, that is positive logic AND gate equal to negative logic OR gate. Consider the table shown on the slide. Here A and B are inputs and Y is output. When both A and B is low, or if one of the input is low, the output is low. When both the inputs are high, output is high. The second table shows that 0 0 is equal to 0, 0 1 0, 1 0 1 and 1 1 1. So, the first table shows you the signal value and the second table shows you the logic value. Let us see the characteristic of logic families. These characteristics are common for all the logic families. So, let us start with the IV characteristics or IV requirements of logic circuits. Now, this slide and next slide shows you how the input current, input voltage and output voltage are referred when the logic level is high and logic level is low. For the high level input current, it is referred as IIH, and you can see in the diagram that it is the current which is going into the gate. High level output current IOH is the output current when the output is high logic level. High level input voltage is the voltage when input is logic high or logic 1, and high level output voltage is VOH, that is when the output voltage is logic 1. Low level input current is referred as IIL. Low level output current is referred as IOL. Low level input voltage is referred as VIL. And low level output voltage is referred as VOL. Next characteristic of logic family is Fanout. It specifies the number of standard gates or loads that the output of the gate can drive without affecting its normal operation. It is the number of similar gates which can be driven by a gate. High fan-out is advantageous because it reduces the need for additional drivers to drive more gates. The maximum fan-out of an output measures its load driving capability. The delay offered by a gate increases with the increase in fan-out. Next characteristic of logic family is fan-in. It refers to the number of inputs of logic gates. It is decided by the input current sinking capability of a logic gate. Next characteristic is power dissipation. It is related to the power requirement of that logic gate. It is proportional to the heat generated by the system. Excessive heat dissipation increases the operating temperature and causes the gate circuitry to drift out of its normal operating range. Next characteristic of logic family is the propagation time. This is the time required for the input to produce the output. It is characterized by rise time and fall time. Rise time is defined as the time required to rise the voltage from 10% to 90% of the maximum voltage of signal. Fall time is referred as the time required to fall the voltage from 90% to 10% of the maximum voltage of the signal. Consider the diagram shown on the slide. You can see one input signal and one output signal. There is a time delay between the input and output referred as TPLH. TPLH is a delay time before output changes from low to high. Similarly, TPHL is the delay time before output changes from high to low. This is the most important parameter, that is figure of merit. Figure of merit is equal to the propagation delay time expressed in nanoseconds multiplied by the power in milliwatt. A low value of speed power product is always desirable. If it is desired to have high speed, that is low propagation delay, then there is a corresponding increase in the power dissipation and vice versa. Let us take one example for this. Let's suppose IC has the average propagation delay of 20 nanoseconds and average power dissipation of 5 milliwatt. Then the figure of merit, that is the speed power product, is 100 picojoules. Next characteristic of logic family is noise margin. The circuit's ability to tolerate the noise signal is referred as the noise immunity. Noise signals may cause the voltage at the input to a logic circuit to drop below VIH or rise above VIL and may produce undesirable operation. A quantitative measure of noise immunity is called as noise margin. On the slide, you can see the values of VOH mean, that means the minimum output voltage which is referred as high, that is logic 1, and maximum output voltage which is referred as low, that is logic 0, and the range between VOH mean and VOL max is disallowed output voltage range. You can see the window between the logic 1 and logic 0 of output, which corresponds to the logic 1 and logic 0 of input. You can see VIH mean as the minimum input voltage, which is referred as logic 1, and VIL is the maximum input voltage, which is referred as logic 0. So, the difference between the VOH mean and VIH mean is the noise margin. Similarly, the difference between VOL max and VIL max is also a noise margin. Typical values of noise levels. Difference between the worst case output voltage of one stage and worst case input voltage of the next stage. Greater the difference, the more unwanted signal that can be added without causing incorrect gate operation. A logic circuit with an input at the voltage level within the intermediate range will definitely produce unpredictable output levels. Noise margin in 2.5 volt minus 0.8 volt is equal to 1.5 volt for the TTL logic family. Let us see the evolution of logic families. Consider the basic logic circuit, which is a diode transistor logic. Basic components used in this logic circuit is diodes and transistors. Consider the basic NAND gate using diode transistor logic. You can see here 2 diodes and 1 transistor and some resistors. Let us verify the truth table using this particular logic circuit. Let A and B both 0 0. So, the diodes D1 and D2 both will be on, but the transistor will be off. So, output will be logic 1. When A is equal to 0 and B is equal to 1, then diode D1 is on but D2 is off as it is reverse biased, and transistor will be off. So, output will be logic 1. When A is 1 and B is 0, then D1 is off and D2 is on, and therefore the transistor is off, therefore output is logic 1. When both A and B are 1 1, both the diodes are reverse biased, and hence transistor will be on and output will be logic 0. Consider the next logic circuit, that is resistor transistor logic. Basic components used are resistors and transistors. You can see on the slide the circuit diagram. It consists of resistors and transistors only. Let us see how it works for NAND gate. When both A and B are 0 0, then the transistor will be off and output will be 1. When A is 0 and B is 1, the transistor will be off and output is logic 1. When A is 1 and B is 0, again transistor is off and output is logic 1. But when both are 1 1, that is A equal to 1 and B equal to 1, in that case the transistor will be on and output is logic 0. Let us conclude this session. Importance of logic families are discussed in detail during this module. Depending upon the components which are used for the fabrication, logic families are classified into DL, TTL, CMOS, etc. And the most important part is one has to use the same logic family, because the complexity and compatibility of the logic circuit is the main issue. Different characteristics of logic families like noise margin, propagation delay, IV requirements, fan in, fan out are discussed in detail. Figure of merit, that is the speed power product, is very important to decide the performance of the logic family. Evolution of logic families are also discussed in detail by considering suitable example. This ends with the module. I am signing off for this module and we will meet in the next module. Thank you very much.